Hey guys, today we are going to talk about logs. Woo!
It's long, long, it's big, it's heavy, it's wood. It's long, long, it's better than that, it's good.
Alright, I know you guys are thinking about, what do I care about big, heavy pieces of wood? Today we're going to talk about logarithms. Okay, and I know that sounds scary and it's not part of the 7th grade math curriculum. Okay, it's actually a big part of the math curriculum in Algebra 2. But I think it's an important concept that we need to understand a lot of the data that's out there about this COVID-19 situation. So I just wanted to do a quick little overview of logarithms. Like I say, you haven't learned about them yet in school. Now, human beings are actually kind of hardwired to think in sense of logarithms. You come into kindergarten thinking in logarithms. We spend elementary school trying to make you unthink about logarithms. And then we spend high school trying to reteach you logarithms. So, anyway, but it's a mathematical concept that we use to understand how numbers change when they change very quickly, when they change exponentially. Okay, so a logarithm is about the idea of how many times you have to multiply a number by itself to get another number. Okay, and that allows big, rapid changes, exponential changes to be understood in common terms. Okay, so to explain this a little bit more, we're going to go back to the computer.
To understand logarithms, we're going to be talking about exponents. Just as a quick review, exponents are when you multiply a number by itself a certain number of times. Okay, so how many of that number you have multiplying together is going to tell us our number for our exponents. Okay, I know it's a little bit of a review. So a classic example is finding the area of a square. 3 times 3 is 9. So if I need to find the area of the square, it's going to be length times width, which is 3 times 3. 3 times 3 equals 9. Right? Another way I could say that is 3 squared equals 9. So I have 2 3's, 1, 2 3's, multiplied together is going to give me 9. Okay? Similarly, if I've got a cube, then if I want to find the volume of the cube, I'm going to say 3 times 3 times 3 is going to give me 27. Right? So I've got how many 3's here? 1, 2, 3. So I have 3 3's. 3 times 3 times 3 is equal to 27. Right? Another way to write that is 3 to the third or 3 cubed. This is telling me I have 3 3's multiplied together to get my 27. Now, exponents aren't just going to be used in finding area. We can also use them in functions in a lot of the same way we've been doing proportional relationships and we've been graphing non-proportional relationships. Later on in your academic careers, you're going to be looking, particularly in algebra, you're going to be looking at exponential functions. So these are functions where your result is y is going to be equal to a value that goes up by the x, right? And that means that it's exponentially expanding. And you guys notice that this kind of has a pretty steep curve right here. You guys see that? How it's going to go up and up and up and up and up and up. That's a part of being an exponential relationship. Okay? Remember, this is about exponents and how much those exponents are going to make this situation change. About change. They're about the relative change. How do I get from one number to another number? How many times do I have to multiply a number by itself to get to that other number? So, like 2 to 8. How do I get from the value 2 to the value 8? Well, I could say 2 plus 6 equals 8. Right? 2 plus 6 equals 8. I think we're all pretty familiar with that. Or I could say 2 times 4 equals 8. I think we're all pretty familiar with that, right? 2 times 4 gives me 8. If I have 2 groups of 4, that's 8. Or if I have 2 and I add 6, that's going to give me 8. Now, we could also look at it exponentially to say 2 times 2 is 4, right? And then 4 times 2 is 8. Or another way I could write that is 2 to the third is equal to 8. So 2 cubed, 2 times 2 times 2, is equal to 8. Okay. Now I could also write that as a logarithm. Okay, so 2 times 2 times 2 is 8. So we had to multiply 3 sets of 2's to get 8. So my logarithm is 3, right? It's essentially telling me what exponent I need to go from 2 to 8 exponentially, right? So 2 times 2 times 2 is equal to 8. So my log with a base of 2, 8 would be equal to 3. Okay? Log with a base of 2, 8 would be 3. Now, theoretically, we can have logs with all sorts of different bases, and we do have logs with all sorts of different bases, but generally we're going to be using the common logarithms, which is base 10, because we have 10 fingers, we have 10 toes, and that means we have 10 digits, right? 10 digits in our numerical system makes base 10 really easy. So our common logarithms are with a base of 10. So this is set up when I say, okay, 10 times 10 is 100, right? And then 100 times 10 is 1,000. So I've got a log of 1,000 would be equal to 3, right? I think we can kind of follow that. 10 times 10 is 100, and then 100 times 10 is 1,000. So if I have a log of 1,000, that would be 3 with a log with a base 10. Okay, and that's usually what is being used on a lot of these logarithmic scales on a lot of the graphic representations that we're seeing with the COVID-19 stuff. So this is not a COVID-19 graph. This is just a graph pulled out of a textbook here. So notice that it starts at 0.1, right? And the distance from 0.1 to get from 0.1 to 1 is the same as the distance it goes from 1 to 10, which is the same as the distance it would go from 10 to 100, and the same as the distance it would go from 100 to 1,000. And notice the scale in the middle is different too, right? So the same distance it goes from 1 to 2 is the same distance that it's going to go from 10 to 20, right? You notice these scales, it's getting smaller and smaller and smaller as it's getting closer and closer to the bigger numbers, right? So I've got the same distance from 1 to 2. Half of that distance is from 2 to 3, from 3 to 4, from 4 to 5, from 5 to 6, from 6 to 7, from 7 to 8, from 8 to 9, and then finally from 9 to 10, it's just barely a little bit, right? And what that means is the amount of change down here on the bottom is a lot of relative change, but very small in terms of absolute values, okay? And the numbers up top are lots of absolute change, but is a lot less relative change. So it's meaning it's changing relative to itself less, okay? To make this a little clearer, I do want to pull up some of these COVID charts, okay? I've been looking at some of these charts. Here we have a graph that's on the COVID-19 cases, okay? And this is on a standard linear scale. So it's where each thing is worth the same amount. Each value is worth the same amount. So it's going up at the same amount for each line, each tick mark essentially on the graph, right? And we notice that we have kind of these general lines. If I follow the world's numbers, it's going to go up and up and up and up and up and up here, right? At this point, this is a standard exponential curve. You're going to spend a good amount of, particularly Algebra 1, talking about exponential curves and parabolic curves and some other stuff like that. But right now, we're going to look at how that exponent fits there, right? And I've also got all the other countries. I've got not all the countries in the world. I've got the United States. I've got Italy. I've got China and Peru on here. And I can kind of get some sense of how it's doing, how this virus is affecting these different countries here. But it's not going to be as effective on this scale as it is. We're going to see a better picture when I come over here and click on if I come over here and click and turn this into a logarithmic scale, okay? And what this is doing is it's putting them all on a scale that's relative to what they already have, right? So I have 1, I've got 10, same distance from 1 to 10, as there is from 10 to 100. Same distance from 100 to 1,000. Same distance from 1,000 to 10,000. The same distance from 10,000 to 100,000. The same distance from 100,000 to a million. Right? And we start off, and we can see that relative speaking here, right? Like we have a big jump here in January in China, right? And in the world, I go from 80 cases to 220 cases, almost 219, right? Which is more than doubling, right? And you can see that big jump, but also realize that's only 120 cases, right? There's 120 cases there that's showing a big jump. When I come up here, if I have an increase, I've got an increase worldwide of almost 2,000, and it's just a little tiny bump, right? Because we're on a logarithmic scale. Relative to the value it was before, it's a much smaller jump, right? And what this does is allows us to see the expansion and contraction relative to other places, right? So I can look here at China's curve, right? And China's curve came up and then it's kind of flattened out, and then relative to the number of cases it had before, it's dropping off, right? The United States, I can follow our curve and we're going up, and we may be leveling off here. That doesn't mean we're not growing, but it means we might be growing at a little bit slower of a rate, right? Likewise with Peru. And you guys can also notice and compare how those expansion and contractions happened relative to the amount that they've already had. I think these types of graphs are really useful here, but in order to understand what they are, you got to make sure you understand the scale, right? So remember, there's a logarithmic scale. So it goes from 1 to 10 is the same distance from 10 to 100, which is the same distance from 100 to 1,000, same distance from 1,000 to 10,000, 10,000 to 100,000, and 100,000 to a million, okay? I just wanted to do this little video for you guys to play with that and kind of be able to understand some of this data a little bit better. You guys stay safe. We miss you guys, and take care until we see you again.